hopefully we can get it finished before you guys have to go. All right, so whenever we're talking about the derivative of a function, we're talking about the instantaneous rate of change of the dependent variable, which is typically y, but does not have to be. They can use different letters for that. With respect to its independent variable, which is typically x, but does not have to be. We'll see a lot of situations where they use a t instead of an x because time is your independent variable. So it's not always the case. So it's your instantaneous rate of change. It is your, change in y over your change in x because it's the slope of your tangent line. So one of the things that is going to be very important and sometimes will even help you answer your question is the units for the problem. So whatever your units for f prime are, it's the unit of f divided by the unit for your x, right? So let's look at some examples of just the unit part of this. So, for example, this question does not ask us to do anything. It just asks about units because units are really important for this. So the function c equals f of t gives the cost in dollars of running a piece of equipment for t hours. So if you think about your function here, t is on your, what would be your x-axis, your horizontal axis, and then f of t is your y-axis. Okay, f of t also can be called capital C. Okay, what is that cost, or the f of t, measured in? It is in dollars. And what is the t measured in? Hours. So I don't know what this looks like, right? But whenever I find a derivative, I'm finding that instantaneous rate of change, right? So I'm looking at what my change in y over my change in x is for that tangent line. So in this case, what would the units be for my first derivative? It would be dollars per hour. Because your dollars are your unit for I want to call it the y. It's the y-axis. It's your vertical axis. I'm going to call it the y-axis. Technically, it's the f of t axis. And this is your unit. Let me just say vertical axis. That would be more mathematically correct. Okay. Does that make sense? Questions? All right. So for the second derivative, this is where I usually see it fall apart. First derivative, kids are usually a little better with their units. Second derivative is where it falls apart. So the second derivative is your instantaneous rate of change of your first derivative, right? So if I did a graph of f prime of t, so f prime of t is here, and this is t, and I am not going to try to actually make it accurate, but we'll do something here. May not match that one so well. and this is f prime of t. The t is still measured in what? Hours, specifically for this. What is f prime measured in? Dollars per hour. So if I find the slope of a tangent line here, and I do my change in my y over my change in my x, then what are the units for my vertical axis? Dollars per hour. And then what are my units for my horizontal axis? Hour. Now, there's a few ways that you can write this. I suggest just writing it this way. I mean, technically that's okay. It's dollars per hour per hour. I suggest just doing that. However, if I make this a fraction, this is dollars per hour divided by hours. And when I have a complex fraction, what do I have to do? Flip the second and multiply. So this would be dollars per hour times 1 over hours. What do I get when I multiply those together? On the top I'll have dollars. On the bottom what do I have? Hours squared. So another option, this works, dollars per hour, dollars per hour squared also works for that. What I see kids do wrong a lot of times if they use that square is they put it in the wrong spot, especially if it's like a feet, yards, something like that, because cubic feet makes sense. Square dollars don't really make the most sense, right? But cubic feet would, or square feet would make sense, but that would not be correct in this context. Yes?
So would that be like giving you the acceleration of the ball?
It's like the acceleration, yes. So it's telling you how quickly your rate of change is changing. It's the rate of change of the rate of change there. So if you have like a positive rate of change and then also a positive second derivative, it's telling you that not only are you increasing, but you're increasing more and more and more quickly. Think about that second derivative tells you like concavity. So if you're thinking about the graph, if you have a positive first derivative but a negative second derivative, your value's increasing, but it's concave down, so it's increasing less quickly there for that. So, here's another one. The time it takes to run a distance, d, is given by the equation t equals r of d, where t is measured in hours and d is measured in miles. And for this, they're asking us for units for r prime of d and also r double prime of d. Now, this is backwards from what you would normally think of, so it makes it a more difficult problem. When you see miles and hours in a problem, what do you want to use for units? I want to use miles per hour. I want to just write down miles per hour for part A, miles per hour for part B. But you got to pay attention to the way they've given this problem. What is your independent variable? What's your horizontal axis? Okay, look right here. What's inside of the parentheses? That is distance. This is your independent variable. So for this problem, D is on your x-axis. Your distance is on your x-axis, and that is measured in miles. And then T is on your y-axis. And what is it measured in? Hours. Okay, so what are your units for A? hours per mile. So this is sort of backwards from normally the way we think about time and distance, right? Typically, we would think of how many miles you could travel in 1 hour, miles per hour. This one is telling you how many hours it takes you to travel 1 mile, right? So what would the units for our double prime be? Hours per mile. Or you could do hours per mile squared. Be careful with that, though, because I see so many kids put the square in the wrong spot. Does that make sense? You gotta be careful. I like to draw myself the X and Y axis and label those things so that I can keep it straight for that. Okay, so another thing they're going to ask you to do pretty often is they're going to ask you to describe the meaning of something. So still, this one doesn't even have a problem in it, right? Like it doesn't even have an equation. It tells us the length of a scarf is given by the function L equals S of T, where length, L, is measured in centimeters and time, T, is measured in minutes. What is the meaning of S prime of 7? So, if I think about a graph right here, I am going to have what variable is on my x-axis? T, which stands for time, and it is measured in what? Minutes. Okay? And then I could call this either L or S of T. What does it stand for? Length, and what's it measured in? Centimeters. I think the units help answer this question because they're asking for S prime of 7. So the units would be centimeters per minute. So what is that telling you about this situation? I would say, I think after 7 minutes would be okay. I would probably say at 7 minutes. You want to be really careful right here on your language. Like, I think after 7 minutes would still be okay because it mostly still implies just a single time. You definitely don't want to say something like over the first 7 minutes because that is not implying a single time point. It's like an average rate of change. So you want to say at 7 minutes, okay? At 7 minutes, what's happening? Right, the length of the scarf and if we knew what the number was, we could say increasing or decreasing. Let's hope it's increasing. But we could say increasing or decreasing. In this particular case, since we don't know whether it's a positive or a negative number, we'll just say is changing. At a rate of S, I'm going to just call it S prime of 7 centimeters per minute. And so if you actually had a number for S prime of 7, if it was 10, at 7 minutes, the length of the scarf is changing at a rate of 10 centimeters per minute. Probably wouldn't be 10. You would really be fast at your knitting if you were sending this. Maybe it could be a machine. Yeah, it could be a machine and not a person. This is a person.
Really experienced.
Yeah, really good. Yeah. Yeah, like an 80-year-old lady with no arthritis.
It seems hard.
It is hard. I like to do stuff like that. I'm not very good at knitting. I can knit, but I'm not very good at it. I can crochet a lot better. I think it's easier. If you'll know what kind of wild time I had in college, I learned how to do it in college. So, yeah, I did. Sometimes I just like stay up all night working on my blanket that I was making. So, it's pretty wild times back then.
I think they're more wild now.
Might be.
I won at my Dirty Santa. I won a crochet kit. So I'm excited.
You should, yeah.
I actually bought it to take as my gift, and I won it back with her.
Yeah. Yeah. It's so like, it's like kind of calming. It's just like you don't have to think all that hard about it. Now, you kind of run out of things to make after a while. You're like, I don't need another scarf and blankets take a really long time.
It's like the whole thing is ruined.
Yeah.
Figure it out until later.
Yeah.
I don't have enough.
That's why you gotta be good. Yeah. But I do enjoy it. I might make something over Christmas. Okay. All right. Okay, this one actually has an equation. I believe. No, I think we can do this one without a calculator. Well, no, we'll need a calculator. Mostly because of our input is 10 right here, and we can't do trig with a number like 10. We would need like pi over 4 or something for that. So this will be calculator, so you can pull up Desmos if you want, or you can just look at what I've got. Either one is fine. Let's see. All right, so let's go ahead and type in this function. Oh, I don't know about Desmos and T's. I think we'd better go with X. Although I know why I'm not getting anything. I keep clicking on the one I use for Math 3, which has degrees as its default. I have not seen, they haven't like shown exactly the like version of Desmos that will be on there, but I feel certain that they will make the default radians on that one because you have to use radians for the whole calculus test, so I don't think you'll have to worry about that. So I've got this particular one. I'm looking at 10 a.m. So I'm looking about right here, and I'm looking for the slope of that tangent line, right? And so it's really easy on Desmos. Just type in h prime of 10, and it'll give you the value right there. It's 0.643. So if you're doing a problem like this, and it is calculator active, you do not have to show that you plugged that number in any way except for h of 10 equals, I'm going to use squiggly equals because I rounded, 0.643. Thank you, h prime of 10. So you don't have to find the derivative, although this is not a difficult derivative to find right here. It's pretty simple to do it by hand. You do not have to find the derivative, but you do need to label it as h prime of 10 to let the grader know what you were typing into the calculator. If you just put 0.643, you may not get full credit for that. You need to label it to let them know what you were typing in. But if you can do it very simply on the calculator, you're allowed to do that. You don't actually have to find h prime. You don't have to show that you plugged in 10 in any way other than just labeling it h prime of 10. So, in this case, on that graph right there, I'm going to put the graph over here. I shouldn't have even used this one. It won't let me put the pictures in. Let's go over here. Okay. Gigantic. Okay, so we're thinking about, on this graph, we're thinking about this point right here. We've got this line. We know its slope is 0.643. What should go on my x-axis? What's that measured? It is t. And what's it measured in? Hours. Okay? And h is my other variable. It goes here. What's it measured in? Feet. Okay? So, whenever we're talking about this, we first need to tell the time that it's happening. So, at 10 hours, what is happening here? We're going to be talking about the height of the water because that's our equation, right? The height of the water what's happening to the height of the water there? It's increasing. Now, how do we know it's increasing? Slope of your tangent is positive. So, height, if we had a negative number right there, it would be decreasing. And you can see it on the graph as well. The height of the water is increasing at a rate of 0.643. What are my units? Feet per hour. Okay, questions? Something important here. On the last problem, we did not say increasing or decreasing. We said changing because we didn't know the sign. The best practice on this is if your derivative is positive, say increasing. If your derivative is negative, say decreasing. You could get away with the height of the water is changing at a rate of 0.643 feet per hour. You get away with it. If you say it's increasing, that is better because that's more specific. What you cannot do is if you have a negative rate, you can't say it's decreasing at that negative rate. That is incorrect because the decreasing and the negative like cancel each other out, and then it's no longer a correct statement there. So be careful with those. All right, let's look at this one. This one, another one that's definitely calculator active. So let's graph this one. All right, so S of x equals 234 e to the negative 0.05x plus 200. And we'll make this full screen. We're probably going to need to zoom way out. Zooming out might not work great. Oh, that works pretty good. So here's our graph. For this, they are asking us to find S prime of 15 and then also S double prime of 15. So we can just type in S prime of x, or S prime of 15 and S double prime of 15. I think that works, yeah. So, for this gives the weight of sand in a storage container after X days, where weight is measured in tons. We're supposed to find S prime of 15 and explain what it means, and then also S double prime of 15. So, in this graph right here, when I'm looking at this, I want it to let me write, but it won't over here. What is our X measured in? Days. And what is our S of X measured in? Tons, right? So the units for first derivative will be tons per day. Okay? So whenever you do a problem like this, you want to say S prime of 15 equals negative 5. Let's do squiggly equals because I'm around 5.527. That squiggly equals is not necessary, but when you round, it is more mathematically correct to do that. It's also helpful to remember that you did round there if you need to use it later for that. So negative 5.527 is what we're looking at here. So we would say if we're, in this case, at 15 days, or I probably would say on day 15, the weight of the sand in the container is, all right, are we increasing or decreasing? What? Decreasing. At a rate of, no, right here, 5.527 tons per day. Notice I did not put the negative with that one, right? Because I already used the word decreasing, which tells me that it's negative. This would be the preferred way to write this. Depending on the rubric, they might take is changing at a rate of negative 5.527. They would take that. But if you say that the weight of sand is decreasing at a rate of negative 5.527, it will be counted wrong because decreasing and negative cancel each other out. There. All right, now I always think second derivative is confusing. It's like acceleration. So you can think about driving in a car, whether you're speeding up or slowing down, sort of, here. But to me, it's a little confusing whenever you're thinking about other contexts. So the first thing you'd want to do is just say S double prime of 15 is approximately 0.276. It's okay. They won't count off for that, even on a free response. As long as you are correct to 3 decimal places, it's fine. I like to do it just to remember that I rounded, but you don't have to. I think they're going to count that wrong because it's not really increasing. If you say changing at a negative rate, I think you can get away with it. But I think if you say increasing at a negative rate, that like you're not showing a very good understanding of that, and they're not going to give you credit for it. For that. And for decreasing at a negative rate, definitely it's a no. I don't think they take the increasing at the negative. All right, so what are the units for that? Let's go ahead and just do the units. That helps me think about it sometimes. Tons per day. Per day. Okay, so in context of this, a second derivative is a rate of change of the rate of change, right? So what we want to say here is on day 15, we'll start with that. We're not talking about the weight of the sand, we're talking about the rate of change of the weight of the sand, right? So the rate of change of the weight of the sand in the container is increasing at a rate of 0.276 tons per day. Now, what's important for this, if you're talking about second derivative, you're talking about the rate of the rate, right? So you shouldn't be talking about the weight of sand increasing at a rate of. That'd be first derivative. It's the rate of change of the weight of sand is changing at a rate of. You should see rate there twice whenever you're doing this. My swimmers have to go. Here is okay, and I'll keep recording so y'all can just like fast forward to this part if you need to. Okay. All right, questions there? Good luck, guys. All right. There almost always is a in context rate of change problem on the exam. Almost always. Sometimes it'll be like a rate in, rate out sort of thing that we haven't really looked at yet, but there's almost always one of these. So here's an example of something that you might see. The depth of water in a rain gauge is given by the twice differentiable function, capital R, from 0 to 24, where R of t is measured in inches and time is measured in hours. Values of R prime of t, the derivative of R, at the selected values of time are shown on the table in the table above. It is known that the graph of R is concave down for 0 to 5. And so we've got our table here. A says, is there a time from 0 to 24 at which the depth of the water in the rain gauge is changing at a rate of 0.5 inches per hour? Justify your answer. So we need to know if the rate of change of the amount of water in the rain gauge, which would be which function? We're doing the rate of change of the rain. That's R prime. We know R prime of t is 0.5. What should we use for that? You would be correct if they had given us the table for R of t. this one is not a mean value theorem problem. This one is just a intermediate value theorem problem. Because we already have r prime of t, and r prime of t is continuous because r is twice differentiable, right? So this is continuous. So if we go from 0.3 right here, or really anywhere you can pick, and we go up here to 0.55, did we have to pass 0.5 at some point? We did. So this is intermediate value theorem. If they had given us the table for r, we'd have to do a mean value theorem to talk about r prime, right? Because we'd be talking about the derivative. But they gave us r prime, and they're asking us about r prime. So we're just using intermediate value theorem here. So to do intermediate value theorem, you have to do the conditions for what's happening here. So, so we would say that r, first we will get a pen instead of a highlighter. Then we will say that r prime of t is continuous since r is twice differentiable. Okay. Now, it does not matter which value you pick. Really, you can pick any value besides r prime of 15. You have to use this one because this is the only value where you go above 0.5. You can say, therefore, since I'm going to pick maybe r of 12. R of 12 equals 0, which is less than 0.5, which is less than my 0.55, which is my r of 15. Oh, they should be r primes. Thank you. Now, this part right here, r prime of 12, you can like literally use any other point on this graph except for r prime of 15, right? So that could change there, and you can still have it right. So since you're below 0.5 at one point, and then you're above 0.5 at another point, we can say by the intermediate value theorem, r prime of t equals 0.5 inches per hour at least once. Hello? Yes, thank you. That's you, Joshua. Alright, at least once on, technically right here, it'd be 12 less than or equal to t less than or equal to 15, and I would put and thus also 0 less than or equal to t less than or equal to 24, since that is part of that interval. I think if you skip to the conclusion of just from 0 to 24, you'd probably get away with it here. But technically, since you're just considering from 12 to 15, it's this interval, which is part of the bigger interval they're looking at, and would guarantee that same outcome. Okay. Questions? Okay. The second part of this asks you to approximate the second derivative of r at 16.5. Show the computations that lead to your answer, and then explain that meaning and context of the problem. So, first of all, what are we going to do to estimate r double prime of 16.5? Average rate of change between 15 and 18. So we would say r double prime of 16.5. Here, it's really important for you to put the squiggly equal sign because it means approximately. I say really important. I don't think they count off for it on the free response part of the AP exam, but it's what you're gonna be way off. This is just an approximation. So mathematically speaking, it's really important for that. And so your points are 15.55 and 18.4. So I'm going to do 0.4 minus 0.55 over 18 minus 15. So you will get negative 0.15 over 3, which is going to give us negative 0.05, I believe. What are the units on that? It'll be inches per hour per hour. Because your y is inches per hour, and then you have to divide it by the x, which is hours for that. But you have to explain it in context of the problem. So what is r anyway? What's r? It is our function. What is it measuring? Okay, the inches of water in the rain gauge, right? So we would begin with at 16.5. Is this hours? Yeah, hours. Now we're doing a second derivative. So r is water in the rain gauge. R prime is rate of change of the water in the rain gauge. R double prime is rate of change of the rate of change of water in the rain gauge. So the rate of change of the amount of water in the rain gauge yes. The rate of change of the amount of water in the rain gauge is, are we increasing or decreasing? Decreasing. At a rate of negative 0.05 inches per hour. Oh, yes. Thank you. I was just testing you there to make sure that you're paying attention. Because it would be incorrect to say decreasing and throw the negative in there. Good. Yeah, you got it. You caught my trick that I totally meant to do right there to check if you were paying attention. So I probably should add the word the rate of change of water in the rain gauge is decreasing at approximately approximately a rate of 0.5 inches per hour, since technically this is an estimate and not the actual amount. Although that's another word. If you leave it out, they're probably not going to count off for that here. Okay, questions? Whenever you've done a second derivative, look at your explanation, and you should see the word rate twice in most cases. There could be another way you could explain it where you don't, but it would be trickier. All right, so you should be talking about the rate of change of the rate of change for that. All right, here is is this our last one? This is last, right? Yep. Okay, so this is calculator active, big time calculator active, because that is a crazy equation. I am not going to use the E. I'm just going to call it f of x equals 0.5 times e to the 2 sine. Oh gosh, typing this in is really hateful. You got to do sine of 0.1t squared, because I don't think it's going to let you do that. Sine squared of, oh, and don't use a t, use x. Squared. Alright, and then this is down here plus x. Plus 50. So notice right there where you got that sine squared, it's not going to let you type it in that way, I don't think. Let me make sure that's true. Okay. Actually, maybe it will. Desmos might let you do that.
There's an X right next to it.
Yeah. Oops. Desmos actually might let you do that square, though. Because that right there, I believe, is the correct graph. Okay. Never mind. Type it like it looks. Desmos is so much better than... You can type it like it looks. I think it's going to work. Okay, I can't see it now, but it's got a plus 50 on the end, so we'll like that graph. It's kind of weird looking, isn't it? All right, so this models the percentage of students who pass the 8th grade math exam in North Carolina from 0 to 50, where T represents the number of years since 1980. We're supposed to find E prime of 15 and interpret its meaning. So I call this F prime, so F prime of 15, and we get 0.603. So in context of this problem, at 15, what am I going to say? I probably shouldn't say at 15 years, because what does T represent? Years since 1980. So what year is it?
1995.
All right, so in 1995, the percentage of students who pass the 8th grade math exam is, are we increasing or decreasing?
Do we have to put NMC?
Probably not on this one. It wouldn't hurt, but if this is the FRQ question, no, they wouldn't count off for that. Now, if they had a problem where you're comparing North Carolina and Georgia, and there's two equations, definitely so. But if it's the only equation, I think it'll be fine, like this. But it wouldn't hurt to put it. Are we increasing or decreasing? Increasing. At a rate of 0.603, what units? It's not number of students. It is per year, but it's not just the number of students. It's the percentage of students per year. So at a rate of 0.603% per year. And you probably should have written up here E prime of 15. Always do this like if it's a free response question. It just depends on what the rubric looks like. But sometimes depending on how they give the points, they may be looking for this. Always put it just like as a safety net. There. Okay, questions? Okay, your assignment for tonight.